nice to meet you. As Steve said, my name is Daniel. Professionally, I work with anything related to radios and satellites. I'm a freelance contractor, and I work in satellite communications and other things. Some of that involves radio, some of that doesn't. Um, Besides that, I've also been collaborating with SETI and with the Allen Telescope Array for 5 years back, I think, or 4 or 5 years, uh, to learn about SETI, to engage with interesting people. And I have a few slides today to introduce you to what GNU Radio is. And probably these are the only slides I will have in the whole summer, because the rest of the tutorials is intended to be very hands-on. We will be using GNU Radio Companion, which is a graphical application, to build some examples and some applications so that you can understand better how signal processing works and how it can be applied to radio astronomy and SETI. If there are any questions, just you can interrupt me at any time. The whole point of making these tutorials, not in person, but online, which is the next best thing if you are 10,000 kilometers away, is that you can engage with me and ask questions, and this can be a conversation.
Daniel, we
So,
have a little bit of a window blocking the top right of your slides there.
top right. Oh, why is that happening? Let me try to. Oh, yeah, I see. That's the other thing. Yeah.
Oh, yeah,
Is that gone now?
Yeah.
Okay, great. Yeah, for me it was behind my window, so it doesn't make any sense, but that's what Zoom does. Thank you. Okay, so GNU Radio, you might have already heard about it. You might already have it installed in your computer if you succeeded. If not, we can troubleshoot either on the break. We are probably going to run for an hour, then small 5-minute break or so, and then the rest of the hour. And if you still don't manage, just contact me on Slack, and we can get it sorted out. So GNU Radio is an open source framework. That means it's not a complete application. It's building blocks for you to build larger things, for you to build applications. It does digital signal processing. So that means we are doing math on our computer, basically, digital calculations. It is mainly intended for radio applications, and that can be radio communications. You can think anything these days is wireless, right? So your cell phone has Wi-Fi. It also has the cell phone signals. There's television. There is all sorts of other stuff, satellite communications. Those fall under radio communications, and radio can be used to build, for example, a Wi-Fi radio or LTE radio, which is the 4G cell phone standard. It can also be used for other radio applications, such as radar, which is not communication. It involves transmitting radio pulses or radio waveforms and seeing how they reflect on some targets. Or radio astronomy, so studying the natural radio emissions from celestial objects. SETI, which is maybe also a form of communications, unintended communications perhaps, but it's also probably a form of communications. I would put it under the communications category. So anything related to radio, really. And it is also useful for applications which have similar mathematical operations. I've seen people using GNU Radio for things related to audio processing or music. There is someone who built something like a guitar effect toolbox, so to say, out of GNU Radio. And there are even people in Germany using GNU Radio to monitor particle accelerators, because they have the particle accelerator. There's a beam of ions going around the accelerator, and it goes around many millions of times a second. And so every time it passes through a sensor, there is some kind of pulse. And because this is periodic, that's a radio frequency waveform. and they can measure that with software-defined radio, which is connected to GNU Radio, and use that to monitor and control the accelerator. So yeah, whole thing beyond radio. I like to say that there are three aspects to GNU Radio, or three things that come together with GNU Radio. The first of them is a graphical user interface application, which is called GNU Radio Companion. That's the main thing we will be using on these tutorials, and we will see how it looks like. Basically, we have a canvas where we can put blocks in there. We connect these blocks, and by doing that, we are describing how our signal processing system is going to operate. If you have used MATLAB Simulink or any other kind of system design toolkit where you basically connect blocks with a graph, GNU Radio Companion is similar to that. And I would say for 90% of the GNU Radio users, that's the way they engage with GNU Radio. There is also a library of processing blocks, which are accessible on GNU Radio Companion. So we will see there are many blocks which we can use in GNU Radio Companion, but these can also be accessed in C++ and Python. So we can write our applications in either of those languages and use any of the blocks which are available. And these blocks they do an operation. The operation can be something really simple, like add two signals or multiply by 7, for example. Those would be very simple blocks, or they can be very complicated. For example, a complete Wi-Fi receiver might be one of those blocks. If you look at it internally, it might be subdivided into more blocks. But as a user, you might just be dragging and dropping this whole block onto your canvas, and you put a radio frequency signal on the input, and at the output you get Wi-Fi packets or IP packets. And finally, there is also a runtime. So to keep this system working, to run things, there needs to be something between the scenes which moves the data between these blocks, which runs the code, which handles everything. And that's the runtime. We won't be interacting directly with the runtime at all, but just you should know that it exists and it is there. Basically, so that you don't need to write all that functionality. You do not need to worry about how data is moved. That's all given to you. Yeah, is there a question?
I think so.
Okay. So I mentioned there is a library of blocks, but beyond that, there is a whole ecosystem where people write something which is called out-of-tree modules. You can think of them as an extension or a plugin. It can implement new blocks which are not in the in-tree library. And the reason for having out-of-tree modules is that there are some applications which are very specific. So they don't really fit within the GNU Radio that everyone installs on their computer. You might have some very specific signal processing blocks, I don't know, for radio frequency interference detection and cancellation in radio astronomy. And only a few people will want to install that on their machines. So you can have an out-of-tree module which contains blocks to perform those functions. And finally, there are also applications, complete applications that use GNU Radio to do signal processing. And you might even run one of these and not know that they're using GNU Radio. They can look like any regular application. They can have a graphical user interface. And the thing is that, yes, the math and the data movement are implemented in GNU Radio, but everything else is just C++ code or Python code or anything. I can give a couple of examples. One of them is GQRX, and we will be using GQRX shortly. And another one is QRadioLink. So this is an example of a very simple flow graph. We will be doing some more later today, just to give you a quick overlook of how it looks like. So there are blocks. In here on the top left, there's an options block. Every flow graph has such a block. And at some point, we will see what's in here. For the moment, the only important thing in the options block is the name or title of the flow graph. We can have variables, and variables are a way to contain either constants, such as numbers that we are going to use repeatedly in the flow graph and we want to put somewhere. It's just a variable, as in any programming language. And they can also contain formulas. So if we need to calculate something, it is good to put a variable, and instead of putting a value, which is a number, this means 32,000. So the K is for 1,000. We can put any formula which is Python. Most of the things you see on GNU Radio Companion accept any Python code, and you can do calculations, you can call Python functions, and that gives a very powerful system. So here are the blocks themselves. The signal source, it's a block which generates some kind of signal. The waveform can be chosen. In this case, I'm choosing a cosine signal. And then we have some numbers, so sample rate, frequency, etc., etc. So basically, this is a 1 kilohertz cosine, and the sample rate is the one we have from here. So nothing too special. We are generating a cosine. And here we are generating a cosine of a different frequency, 1.5 kilohertz. And then just for the sake of the example, we add the two signals together. So here's a block with 2 inputs and 1 output. And we could do any kind of math operation we want. Just addition is the easiest one. There is a throttle block here. So when we use GNU Radio, there are usually 2 main ways of using it. We can either obtain our data from some kind of radio, which supplies the data in real time, and we will do that today. Or we can run in a simulation where there is no physical hardware, and everything is just software running on the computer. So something needs to set the pace of this simulation, because otherwise the computer is going to run things as fast as possible. The simulation is going to use 100% CPU. If you're running on the laptop and batteries, it will drain your batteries pretty quickly, and that is often not the thing we want. So this throttle block limits the rate at which samples are flowing through here to any given value we put in here. So this is a simulation where we are creating 2 signals of 1 and 1.5 kilohertz, and we are basically constraining the simulation to run at 32 kilosamples per second, or kilohertz. So that means we are running the simulation in real time. I'm realizing that maybe some of the concepts I'm giving here might not make all sense to all of you. I'm talking about frequencies, I'm talking about sample rates, samples. Do not worry, we will see all of that in a practical way. I just want this for the sake of the example, that there are blocks and they can be connected. And so we can describe how a system should operate. And finally, we need to send the data somewhere. So in here, what I have chosen is something called TCP sync. TCP is a network protocol. Maybe you have heard about it. And I'm simply sending this over the network to whichever application might connect to this port, so port 2000. And so basically, with this very simple example, I have a way of generating some signals that then I can use on some network connected application, which could be any kind of application. It could be doing some analysis on those signals. It could be saving the data to disk. We don't really care. Okay, what else? I mentioned it is possible to code with GNU Radio on Python and in C++. When we make a flow graph like this, the way it actually works is that GNU Radio Companion is going to generate some Python code for us. And this Python code is the thing that gets run. But we can also write such Python code by hand. And this is more or less the Python code that gets generated with such flow graph. I have edited it a little bit to remove some things which are not very important. And the main reason why I'm showing this is to show you that this is not so complicated. If you have used Python anytime in the past, and using this as an example, you can figure out how it works. Basically, the flow graph is a class, and everything happens on this init method. We So this inherits from top block, and we need to initialize the top block. Basically, this is boilerplate code you'll have in any of those things if you ever write it by hand. Then we have the variables. So we have the sample rate equals 32,000. Then we have the blocks, and you can see, well, we are basically instantiating one class for each of the blocks. So this is the TCP sync, and it has the parameters it had on the flow graph, throttle, and it uses the sample rate. And this is add, for example. VCC means vector complex complex, and maybe that is something I should mention now. And then we have the signal source, which is generating a cosine wave, 1500 hertz and 1000 hertz. So it's basically the same thing I had on the flow graph, just in Python code. And then, oops, sorry. There's another important thing on the flow graph, which is the connections, these arrows. So we need to describe the connections in Python, and this again is very easy. So we do connect, and for example, signal source, this is output number 0 because the signal source only has one output, and then add input number 0. So that would be this particular connection, output number 0, input number 0, and then we have connect the other signal source. So this one gets connected to the add block on input number 1, and input number 1 is this one. And in this way, you can describe your flow graph. Why can it be useful to write flow graphs in Python code if we can always use this graphical approach? Well, maybe we have a flow graph which is very large. For example, in some of the tutorials and also in the Allen telescope array, we will see antenna arrays, which have many antennas that can be used for interferometry, for example. And the Allen telescope array, for example, has a total of 42 antennas. So I could have one block in here for each of my 42 antennas, and I could put them there. Then if I need to do a correlation, I need to multiply all the pairs of the antennas. So you can imagine 42 times 41 divided by 2 is quite a lot. I don't want to have to draw in here by hand those many multiply blocks. So what I can do is write it in Python, and in Python I can write for loops, and then it is not a problem anymore if I have 42 antennas or 100 antennas or however many. I'm going to write a for loop, and it's going to create as many blocks as I need. So that's one of the advantages of doing things in Python. I said I needed to say something about complex signals. So we will be learning more about why we work with complex signals and why are they useful. And this is a common question because when you think of a radio frequency signal, when you think of the voltage on an antenna, which is the thing that a radio receiver is measuring, that is a real signal. In nature, probably there is no such thing really physically as complex numbers. They are a mathematical tool to make some calculations easier. So there is one reason or several reasons why we use complex signals to represent radio frequency signals, and I will get to those at some point. The only thing you need to know for now is that the color of these ports represents the data type, and blue, which is the port type we will be using more commonly, stands for complex floating point data. So everything here is complex data. Complex means real and imaginary. So that's like the mathematical field of complex numbers. Okay, why can GNU Radio be useful, or some particular applications that can be useful in SETI and radio astronomy? And here I have a few. The first of them is a complete backend for small radio telescopes. And here's, I say small for one reason, which is that GNU Radio intends to be a general application that can be used for anything, but that also comes with some disadvantages, which is that performance-wise, it's somewhat lower performance than an application which is intended for a very specific purpose, such as being the backend of a radio telescope. because if you're writing an application which is just the back end of a radio telescope, you know exactly which operations you need to do and you can optimize them very well. If you are doing a framework which is able to do anything related to radio, it's much more difficult to optimize things. So in that sense, GNU Radio cannot really compete with specific radio astronomy software. In large telescopes, which have very large bandwidths, they have many antennas. So for those, we need to use specialized software. But if we have a small radio telescope and people set this up for education, for example, then GNU Radio is completely fine, and it might actually be easier to get going than something which is more specialized and maybe it needs you to read some documentation or to go on the command line and set up something. What else? So everything which is related to communications or other types of signals you might find while doing SETI or radio astronomy, GNU Radio is a good tool because it actually comes from the communications world and from communications people. So if you want to do radio frequency interference analysis or simulation, you can do that in GNU Radio. If you want to generate some particular kind of signal, I don't know, cell phone signals, and you want to see how these affect your observations, you can use GNU Radio to generate pretty realistic cell phone signals and also to detect them, etc., etc. It can also be used to simulate simpler signals such as technosignatures. We will see some simple examples of technosignatures probably in the next tutorial, but I think you have already seen them. They are narrowband frequency signals that drift in frequency because of Doppler drift. And that is the main kind of technosignature that SETI searches try to detect. So we can simulate that in GNU Radio. And for example, if we are improving a SETI detection pipeline, then we can generate some data sets in GNU Radio to check, does my pipeline detect weak signals? Does my pipeline deal properly with all the Doppler drift rates it needs to deal with, etc. Also, any kind of signal processing algorithm you have in mind, you can write it in GNU Radio. We will see that it's possible to write your own blocks by writing some Python code in some text editor. Basically says, fill in here your math operations in Python. So if you are thinking of doing some signal processing and maybe you are doing that, I don't know, with a Python script or with a Jupyter notebook, or something similar, but you want to go a bit beyond that and you want to be able to run that in real time, connected to a radio or to process some files, GNU Radio can be a good platform for that. And last but not least, for teaching, I think it's an excellent tool for teaching. And this is what these whole tutorials are about using GNU Radio for teaching, signal processing, tools, I would say, which are useful in SETI and radio astronomy. And so is the end of my slides. Are there any questions? Okay, so let's get to more fun stuff. I have in here an RTL-SDR radio, and I think you might have one of those. So probably Steve has handed you one of these radios. They might not look like exactly the same, but they have a USB port, and a port here might be a different connector type where you can connect an antenna. And this is the radio we will be using to sample radio frequency signals on our computer and to do some experimentation in these sessions. So I'm basically going to hook it up. I have a USB cable here, and I'm going to hook it up to my computer and leave it here on the desk. And at first, I'm going to give you a very quick rundown of how these kind of radios can be used. And for that, I'm going to use GQRX, which, as I mentioned, is an application that uses GNU Radio. If you have installed Radio Conda, GQRX is included in Radio Conda, so you should have an icon somewhere, or you can run it from the terminal just by typing in GQRX. If you are on Linux and you have installed GNU Radio from the package manager, you also probably need to install GQRX. It's a separate package, but it's included in most or all Linux distributions. So, okay, I'm going to run GQRX. And because I've run it already, it doesn't show me a settings screen, but I'm going to show you how that looks like. If this is the first time you have run it, or if you have changed your hardware, it will say what is the input device you want to use. And this is the window which appears. And there is a drop-down menu which has entries for hardware we might have plugged into the computer. So in this case, this Realtek RTL something something is my SDR stick I have just plugged in. There are other entries for network connected devices that you might have or might not have. Your computer doesn't know if they are on the network or not until you try to connect. So that's the reason I get all these receivers. I don't have any of these. I just have the drivers installed. And because they are network devices, they show up and they will ask me what is the IP address and all that stuff. But we are not going to use any of them. And something else I want to point out is that in this case, I actually have two different options for my SDR stick. There is this Realtek RTL something something serial number 1, and you can see a very similar entry which says generic RTL, the same number, and then the serial number is the same. And this is actually the same device. It's just different drivers. And you can see, for example, there is a device string that gets changed when I change the device. Here it says driver RTL-SDR. Here it says driver, it doesn't say driver, it says RTL equals 0. So this is just because there are like two different driver options to use with this radio. And usually the two of them work well. The two of them are mostly interchangeable. So my advice is if you have the two options, just test either of them or both of them. And if both work, use the one you prefer. So that's the explanation. Something else we need to set is the input rate. This is also known as the sample rate. And the sample rate is how many samples per second we are capturing. So the way that any kind of digital radio works is by converting an analog signal, which is at the antenna connector, into a digital signal by sampling it in time. It's basically making measurements at very small time steps. And for example, with this configuration, we have 1.8 million measurements of the antenna voltage per second. That's how it works. And why is this important? There's something which is called the Nyquist theorem, which says that the sample rate we set here is equal to the bandwidth of the signal we can receive. So with 1.8 millions of samples per second, we can receive 1.8 megahertz of spectrum. If you have studied any of signal processing, you might remember that it's sample rate divided by 2. That is for real signals. If we are working with complex signals, which is the case here, it's bandwidth equals sample rate. We don't have this divided by 2 factor. So we can choose the sample rate from a list of options. And sample rate, which usually works well, is this 2.4 megasamples per second. We can push it as high as 3.2, but sometimes it doesn't work well. It gives either USB connection issues or it overheats slightly. It can fail, but 2.4 is fine. And if you need 3.2 or are interested in checking out, you can check it out. It's completely safe. You might just hit a problem where data transfer stops running or something like that. And that's pretty much the things we need to set. There's bandwidth, which doesn't do anything for the RTLSDR, which is the radio we are using. There are other radios where an analog bandwidth can be configured here. And LNB local oscillator, which we are not going to use. So, well, I should say this is for frequency conversion. If you have as part of your receive system something that shifts things in frequency, then you can put in here how much the shift is so that the frequency you see in here actually corresponds to the sky frequency. If you remember this, when we get to the Allen telescope array, we we will get back to that because there is frequency conversion going on there. For the rest of the summer, we will not be using any kind of frequency conversion, and so this is 0. And then finally, there's my audio output, and this usually can be set as default. So I can hit OK, and then I have this screen. Let me check. OK. I have checked that the mode I have in here is demodulation off, because if I have selected anything else, then it will start playing back audio, and it might be too loud, so I don't want audio coming out right away. So I can click on this play button, which says start DSP, and this is the spectrum I see. This 1.144 megahertz is the frequency I'm tuned to. And I'm going to tune to another more interesting signal. So this is 98 megahertz. And we can see some signals in here. So here's a signal, here's another one, here's another one. Basically, this is the spectrum. So the x-axis is frequency in megahertz. We can see we have a span of 2.4 megahertz, as we expected from our sample rate. And here the y-axis is power in decibels. And this is known as the waterfall display. Sorry, it's basically the same thing as the spectrum display, but it also has time as an axis. So the vertical axis here is time. You can see that this is scrolling as time goes by. We also have frequency here, and power is represented by color. So these are FM radio stations. And you can see, for example, in here, this is a classical music radio station, and you can see the pattern of the music. So as the music becomes louder, or maybe there are silences in the music, you can see how the waveform changes. And we have a bunch of FM radio stations, and we are receiving all of them at once. That's one of the interesting things of a software-defined radio, is that we can capture a chunk of spectrum and then process all the signals in there, as opposed to, I don't know, regular FM receiver, such as the one you might have in your car, which can only tune to a single FM radio station. And it needs to be FM, it needs to be in the FM band, and it can only do that. So, okay, let me show you how to actually play the FM stations. The thing I need to do is I'm going to turn down the gain, because again, I don't want anything too loud. And here in mode, I can choose wideband FM mono, for example. Stereo also works if the station is stereo, but I can choose WFM mono. And then this thing is the station I'm tuned to. So I can either drag and drop, or I can click. And if I click in here, you can see there's something in here, which is the audio from the station. And if I turn the gain up, we will hear some music.
Liga Juvenil Comunista en 1956 y se divorció 3 años después.
Okay, so it's not music, it's some presenter talking about the music piece, but you get the idea. Any questions at this point?
You got a lot of little spikes across the spectrum there, Daniel. Why is that?
Oh yeah, that's a good point. So I have pointed at the FM stations on the spectrum. Everything else on the spectrum is interference. I'm next to a computer. I have the RTL-SDR next to a computer screen. All of those devices radiate radio frequency signals unintentionally because of how the electronics work. And something I can demonstrate is I've picked it up with my hand, and if I put it, I don't know, next to the screen or something, you will see that some of the spikes change. For example, they are stronger there, and the noise floor is also changing as I'm moving the receiver. So all of that is local radio frequency interference, both the noise floor. So there is always a noise floor. You are going to have noise, which is basically like the minimum level of the spectrum. This would be the noise floor. But then usually, and depending on where you are, what kind of antenna you are using, and what's around you, you can see all of these spikes, which are interference from all sorts of electronics. This is the reason why in radio telescopes, they don't have as many electronics. They don't have any radio frequency transmitters. In some of them, they don't even have microwaves, or they have them in a Faraday cage. So that's the reason. And there's something else in here, which I don't know what it is, but it shouldn't be there. Or maybe it's a weak FM station. I don't know. But yeah, interference. Any other questions?
You mentioned the signals we're reading and are complex. I don't know. I don't know how else to phrase this, but how does that work? Like, because I mean, if you measure the voltage across the antenna, it's going to be a real number. Where does the imaginary part come from?
Okay. Yeah, that's a great question. I'm trying to give a complete answer, but it might not make sense until we have done some more experimentation with this. But nevertheless, it will be a complete answer. So the station in here, for example, is at 98 megahertz. According to the Nyquist theorem, if I wanted to sample this signal, which has 98 megahertz of bandwidth, it's a signal at 98 megahertz, I would need to sample it at a sampling rate which is twice as much, 98 million times per second. And that is very high. It is quite expensive to build such an analog to digital converter. And definitely the $25 SDR we are using doesn't have anything like that. So what it does is it performs a frequency shift in an analog way. It generates something which is called local oscillator, which is a 98 megahertz signal that basically shifts all of these down to zero. It tunes at 0 hertz or at DC, the station in the middle or the frequency in the middle. And then what happens is that 0 hertz is something peculiar because if you think about frequencies, negative frequencies don't really exist, right? Because the frequency is the inverse of the period, and the period is the time that it takes one cycle of something which is periodic. So it's a positive number, it's time, right? So in a sense, negative frequencies do not exist. But if we use complex numbers, they do exist. If you know anything about Fourier analysis, you might know that there are positive and negative frequencies when you do the Fourier thing, the Fourier transform, sorry, which is a thing where you have complex numbers, you want it or not. If you are doing Fourier analysis, complex number come like immediately into the picture. And this is also related to a wheel. So a wheel, if you think of spinning a bicycle wheel or something like that, it has a frequency, how many rotations per second we are doing, or revolutions per minute, or however you want to think about it. But it's not the same thing to rotate clockwise or counterclockwise. So wheel has a direction of rotation. And that is because a wheel is a two-dimensional object and it's related to, it's a real part on the x-axis, imaginary part on the y-axis. So these are all the things going on behind the scenes of why we have complex numbers, why we need them, why are they useful. To summarize, they allow us to represent negative frequencies, which we use for this kind of hardware because it intends to shift the radio frequency signal down to DC, where it is easier, so down to 0 hertz, where it is easier to sample at. But if this is at 0 hertz, then everything on the left needs to be at negative frequencies. So to sample both positive and negative frequencies, we need something which has basically two ADCs. It samples two different voltages, one which corresponds to the real part, one to the imaginary part. I don't know if that gives you more questions or if it's a satisfactory answer. It is somehow tricky to explain without going into more detail, but these are the things which are behind it. It's a great question, by the way.
Yeah, it helped. It helped. I think it'll make more sense once we experiment more, but that definitely cleared it up a little.
And back in the day when, you know, radios, well, I guess radios still are built from hardware, right? I mean, you think of tuning the radio dial, you're changing the frequency of the local oscillator, which is then determining which frequency gets shifted down and sampled.
Yep. Okay, any other questions? Great. So the next thing I'm going to show you is something very, very practical, which is how to adjust the gain on these things, because any kind of receiver or radio receiver has a gain setting. In here, it is called LNA. Go to these input controls, and we can set it all the way down to 0, and then all the signals except for the strongest ones disappear. We can set it to maximum, and then the results can be quite bad because the receiver can be saturated. So we are getting less performance and less sensitivity out of it than what we could. So somewhere in the middle, there is the optimum gain. And the question is how to adjust it, because any kind of thing you want to do with one of these radios, you will need to set a reasonable gain. And I'm going to show you two strategies, which will also allow me to introduce some other concepts. So one strategy is as follows. I'm going to set this to 20 because this is in decibels, because that's like a round number is somewhere around the middle. And the thing I'm going to watch out for is the signal to noise ratio. And let me remove this thing. The signal to noise ratio is what is the strength of the signal, which we can read in here. For example, if we take the peak of the signal, it kind of depends on what kind of music it's playing, but we can say it's somewhere around here. If I go to the y-axis, it's around minus 50 decibels. So, okay, my signal strength is minus 50 decibels. Then the noise floor, which is all of these, basically this level, and you can see that it isn't flat. There is like some roll off here. It doesn't matter. But if I take as a reference this noise level, it's, I don't know, let's call it minus 85. So the difference between those two values is the signal to noise ratio. There are maybe more accurate ways of measuring it, but for the time being, that's enough because we are going to do comparisons of signal to noise ratio when we change the gain. So I said here, this is minus 50, minus 85. So the difference between minus 50 and minus 85 is minus 35. And the thing I want to do now is to increase my gain by maybe 10 decibels and see what happens. So what I see is that everything has gone up by 10 decibels or almost 10 decibels, not surprising because I've increased the gain by 10 decibels. So that's what we expect. It's not going to be exactly 10 decibels because hardware isn't perfect. So if you tell the hardware increase my gain by 10 decibels, it will be close enough, but not exactly 10. And we can do the same calculation and check if we still have 35 dBs of signal to noise ratio, or if it has improved or got worse. And in this case, it's the same. You can do the math, but I think it's the same. We can increase 10 dB more. And now we can see that the noise has increased by more than 10 dB. And actually, if you look at this, it's maybe only 30 dB of signal to noise ratio because the noise has increased more than the 10 dB increase I did. And the reason for that is that the gain is too high and the receiver is beginning to saturate. And if I keep increasing this, then we get worse and worse scenario. So that's one end of the gain scale. We can go to the other end. So I was at 20 before, and then the question we can ask ourselves is, if I go to 10 dB, do I still get 35 dBs of signal to noise ratio? And probably not. It looks like I'm getting even less than 30. And the reason for that is the gain now is too low that signals begin to be drawn out. So you can see that if I continue decreasing the gain, the noise doesn't even move, but all the signals decrease in power, and so the weaker of them disappear. So the conclusion is, by doing this kind of study, the sweet point is 20 dB, 30 dB, something around that. It's never a critical value. You just need to set it to something reasonable. So I think I'm going to go with 30. That's one method. Basically, you have a signal and you figure out how signal to noise ratio changes as you change gain. There's another method which is useful if you don't have any signals to use. For that method, I'm going to grab the SDR, and what I'm going to do is to remove the antenna. So I'm going to disconnect the antenna. And the thing you can see, well, there's still a tiny bit of this FM radio station because this is strong enough that it gets inside the receiver through the metal case and everything, or through my fingers, which are holding the cable, I don't know. But for the rest of the spectrum, we just have this noise floor. And since there is no antenna connected, this noise cannot come from the antenna. The noise is coming from the electronics inside the receiver. Any kind of electronic equipment is not going to be perfect. It's going to generate some noise. So this is called receiver noise. And the thing we want to do is we want to take note of where this receiver noise is. That's minus 90 decibels, more or less. Now we want to connect the antenna. And once I screw it in, we will see that signals appear again. And the noise floor has increased from minus 90 to minus 80. That means that the contribution from the noise coming from the antenna has caused an increase in 10 decibels. And this is kind of the thing we are aiming for. If the increase in noise when we have an antenna as compared to no antenna connected is 10 decibels or more, the noise coming from the antenna is much more powerful than the noise generated by the receiver. And that means that all the signals we see are basically coming in from the antenna. The receiver noise, it's a very small contribution. And so gain is set more or less correctly, unless we are saturating. So that is the rule. For example, we can demonstrate this rule. If I go to 16 decibels, you can see maybe here with an antenna, the noise is at minus 90. And the question is, does it even change if I remove the antenna? And it barely changes. You can see it here, it changed a little bit in color, but not much, and definitely not anywhere near 10 decibels. So that means that with a gain as low as 16 decibels and with this particular kind of antenna, all the noise I'm seeing, or most of the noise I'm seeing, is coming from the receiver, not from the antenna. So my gain is too low that the receiver is degrading my signal quality. And that is how we can adjust gain. In your case, I think it's a similar RTL-SDR, so again, about 30 should be all right. But now you have the means to check it for yourselves. And this really works with any kind of radio receiver. It will also work with an expensive radio, with a radio telescope, or with anything. This is based on first principles. So it applies to anything. Questions about gain settings? Okay, something which I find really cool about these radio devices is that they are inexpensive and they allow you to explore the radio frequency spectrum. It's like putting on some glasses and suddenly you can see a whole new and different world that was hidden before. We can see FM stations here, which is maybe not so interesting. But for example, if I tune to 117.300, I know that in here, where I'm living at, there is an aircraft navigation signal, and the signal is this thing, and it also has these things. Maybe, I don't know, if I put it up in the air, you can see it better. So, and you can see also in here, there's some Morse code, which is the identification for the navigation station. That is how an airplane pilot knows that they are tuned to the correct station. So now you see you are receiving some kind of radio station that you might not have even known that it existed. And there is much to explore. This covers from 20 something or 30 something megahertz up to 1.6 or 1.8 gigahertz. It depends slightly on the model of receiver you have, but it has a very large frequency range. For example, something else I can show is, let's see if this works fine. Where is this? Yeah, you can play with this. So I've done it. I have maybe not mentioned what I was doing. If you want to zoom in frequency, you can put your mouse in here, and with the mouse wheel, then you can scroll. And maybe if you have a laptop, you can also use two fingers to zoom in and out. I don't know. 1090 megahertz, and I'm going to hold it up in the air. You can see a bunch of signals in here. And these are signals which are transmitted by airplanes. They transmit the airplane position, and you might have even seen these kinds of applications, or you can look them up online. If you see any of those aircraft map, which show you in real time where aircraft are located, they are based on receiving these kinds of signals. Every aircraft is transmitting periodically a short beacon signal like this with its own position. And that's basically what I'm seeing. A bunch of aircraft which are flying near here, and each of them is transmitting its position. Something else I should say is there is a record button here. It's this one which I think it has a label. Yes, record and play IQ data. So IQ data is the same as complex data, and it usually means radio frequency data. It's used almost interchangeably. So you can record the raw data that you are seeing to files, and you can say where you want the recording to happen. You can click record. It will put the date and the frequency and everything else for you. And at some point, we will see how to use either GNU Radio or other software applications to look at those recordings. So if you see something interesting, you might decide to record it and have it for later analysis. We will be working on these sessions is there's this GitHub repository, which I already shared the link on Slack. And I will be posting materials here ahead of time, just so that you have them available on the day of the tutorial. You don't need to check this out in advance. And here, well, these are the slides which we have already seen. But here, for example, in RTLSDR, I have this RTLSDR GRC, which is the GNU Radio Flowgraph we will be building now. But usually the way I do this is I build the Flowgraph from scratch and have this one as reference. So you can even, if you have downloaded this repo, you can even open it and you have the final thing. But I think it's more interesting to work from scratch and basically do the whole thing since the beginning. For some of the tutorials, since I have more complex examples, I might do it in advance and just use it or use part of it, because it would take too much time to do all of it in real time in front of you. But for simple ones, I'm going to do it in this way. So To run GNU Radio Companion, we just can type GNU Radio Companion in a terminal, or perhaps you even have an icon. And then we get something like this. I'm going to, yeah, this is the, so this is the RTL-SDR GRC, which is on the repository. And I'm going to build something like that from scratch. And this is, I've pressed the new flow graph. So new flow graph, it always gives me an empty flow graph, and it's called untitled. So the first thing I'm going to do is to save it. Maybe even save is fine. And I'm going to call it RTL-SDR2. So this is the one we will be working on. And I mentioned these options. Block has like some high-level properties about the flow graph. There is the name RTL-SDR2, which is usually the same as the file name. You can give it a title. You can write your name here, other metadata. And there is these generate options. At some point, I will explain what this is. For the time being, you want this to be Qt GUI, which means that you can use graphical user interface elements, which are implemented in Qt. Qt is a graphical user interface library. So that's it. Variables. Every flow graph comes with a variable called sample rate, and normally you use that to set your sample rate. But there is nothing magical about this variable. It's just by convention, and anywhere you need a sample rate, we will use the sample rate variable. Since I mentioned that a good sample rate is 2.4 million, I'm going to type that. And in here, we can type numbers. We can type any kind of Python code. So maybe as a demonstration, I can type 2.4 million plus 1. And if I hover, then I can see the result because it's Python code doing the calculation for me. I could type anything I wanted. This is the canvas. This is the list of blocks. It comes in a tree by categories. So you can see, for example, audio, and there are all sorts of blocks related to audio. There are different packages. So for example, ATA is the Allen Telescope Array. There is an out-of-tree module, which is used to control the Allen Telescope Array. And I have these installed in my machine. Probably you don't, and you only have core. So core are the blocks which come integrated with GNU Radio. All the other ones, these ATA, Azure Software Radio, etc., are out-of-tree modules. So additional packages I have installed in my system, and they come with their own blocks. If you are trying to look for a block that does something you want to do, you can try to search for it by categories. So for example, filters, if you are interested in filtering some signals, or you can even search online. So maybe that's something I should also mention. If you go to wiki.gnuradio.org, this is the wiki of the project. And there are tutorials, there is the list of blogs. So there is a good amount of documentation in here, and it's kept up to date by the community. And yeah, list of blocks. If you are looking for a block that does something, you can see 554 total blocks, and maybe some of them are missing. And usually they come with an explanation of the parameters. They might even have an example. So here it goes somewhere else, and it says here you can do stuff. So this is a good resource for learning and for checking out which blocks exist. Probably better than searching in here. But anyhow, you can also search by name. So if we know the name of a block, for example, add, we know that there is a block which is called add. We can do Control F, which is find. That's probably somewhere on the menus. I don't know, Control F. And then we write add on this box, and it shows everything which is add, which contains add on the name. So for example, this add block. And I can drag and drop, and I can move it, and I can either right click and press delete, or just press my delete key to make it go away. And the thing which I want to use now is the RTL-SDR. And as before, we have two of these blocks. We have the RTL-SDR source. I'm dragging and dropping. We have this SOAP RTL-SDR. Maybe I'm going to decrease the zoom a little bit because that was too much. These are basically the same thing, two different drivers. And because they are two different drivers, they have the parameters organized somewhat differently, but that's the only difference. And you can test both, and probably both of them will work. If one of them doesn't, then no worries, because the other one might. So I'm going to use this one first. And this one I don't need for the moment. So there is a way to disable blocks. We don't need. We either right click and press disable, or we just press the letter D. And the block becomes gray, and it's as if it wasn't present. If you disable a block and you don't see it, then that's because there is an option here which says hide disabled blocks. And if I enable it, it's hidden. And so that's Control D. You might have pressed Control D by accident, or it might come like this by default. I think it doesn't. So usually it's better to leave this disabled. So, okay, let's take a look at the options of this block. We can double click on any block. I think I've done it before with the options without explaining what I was doing. Or we can right click and click on properties, so we can press return. There are different ways of getting to the properties. So for example, double click, and we get this window with the properties. And we can see the output type. So this, again, complex floating point 32. That's the most common data type. There are a bunch of parameters that we don't need to set, and they actually correspond to other different SDRs, because this is from a generic driver which is intended to work with a family of different SDRs. Some of the parameters only make sense for some of the hardware SDRs which are on the market. So for example, this number of motherboard sync, motherboard clock source, etc. And none of those do anything with the RTL SDR you have. They are for other SDRs which have options for that. What things we have? So we have sample rate. And in here we see there is sample rate, which is the same name as this variable. Because in here we can write any kind of Python expression. I can write 1,000 if I want. I can write 1,000 multiplied by sample rate, because sample rate is a variable. So it is like a variable in Python. You can use it by name and it has a value. But the usual way to proceed with the sample rate is you have a variable which is called sample rate, and you put it anywhere that needs a sample rate, you write sample rate. Then frequency. This E6 is megahertz, right? It's a million, so 100 million of hertz. I want to tune to one of the radio stations I was showing, and there's one at 98.8 megahertz. So that's the frequency I'm going to use. And there's a frequency correction. If you measured your RTL-SDR and you realize that it has a frequency error because it has a quartz crystal in there, which is going to have some error, you could put a value in here and correct for it, but it's fine not to do any correction. And then the next interesting thing is the gain. So there is RF gain, IF gain, and BB gain. And the reason for having three different gains is because depending on the SDR hardware, there might be different knobs to control the gain. In the case of the RTL-SDR, there's just a single knob, and sometimes it's slightly confusing which of these three numbers is the one which does something, but I will tell you how to figure it out, and while also introducing something which can be done on GNU Radio, which is basically I want to have something to be able to change each of these three values when I run my flow graph. So what I'm going to do is to search for entry. And there is something called Qt GUI entry. Everything which is called Qt GUI is a graphical user interface element, which lets you interact with the flow graph. And in this case, entry is a text field. So we can write a number in the text field, and that number will be used somewhere to set the value of a variable. So I'm going to make this type floating point, give the default value of 0, and I'm going to call this rf gain. So I now have something which is like a variable. It has a name, it has, or an ID, that's how GNU Radio calls it, ID. It has a default value, which is 0, but it also has a graphical interface element, which lets me change the value. I'm going to copy and paste these 2 times, and copy and paste, it's Control-C, Control-V as usual, or you can copy and paste with right click. And I'm going to do if gain, also 0 by default, and bb gain. Why am I doing this? Because if I come back to the properties, these are the gains which I can set. So if I write here rf gain, whatever is the current value on this entry will be applied to this field. If I then go on the GUI and, I don't know, write 20 in this entry, then rf gain will have the value 20, and a 20 will be passed to this parameter. Something to point out is not all parameters can be updated while the flow graph is running. You might have seen that some of these fields have, they are underlined, basically all of them on the screen. But for example, number of channels is not. So number of channels doesn't have an underline because it can only be set at the beginning of the run. We set it and then we can no longer change it. We would need to stop the flow graph, change it, and start it again. Everything else which is underlined can be changed while the flow graph is running. Often it is for technical reasons that something cannot be changed in real time. For example, the number of channels, the SDR might need to be initialized with some particular number of channels, and you cannot add new channels on the fly, or GNU Radio might need to allocate resources, reasons like that. Ideally, most of the parameters you can set in update in real time. So I've gained BB gain. This is basically a way of giving me access to these 3 parameters and a means to change each of them as the flow graph is running so that I can see the effects of changing them. It's basically the same thing we have been doing on GQRX, except we are kind of building a GUI for ourselves rather than using a ready-made application. So that's it. Antenna, it doesn't do anything because there is a single antenna connector on the RTL-SDR. If you had multiple, this would be used to choose the antenna connector. And bandwidth, as I mentioned, it doesn't do anything. So I have something to receive data from my RTL-SDR. The other thing I want to do is I want to show the spectrum. And there is something called Qt GUI frequency sync. Anything under instrumentation, so that's useful for me to show. Anything under instrumentation Qt are things which can be displayed. They are plots of some shape or form. And there is also GUI widgets. These are usually inputs like buttons, selectors, text fields, etc. And this is how you can build a GUI for doing something. So we can connect these 2 blocks. How do we connect blocks? There are 2 different ways. The first way is I click on one port, for example, the output here. So click, and then I click on the other port, the input here, click, and with the second click, a connection is made. So that's option number 1. I can select the connection with the mouse and then press delete or right click delete and show you the second way of connecting. The second way of connecting is drag and drop. So you click on this one, you drag, you see you have an arrow, and you drop it on the destination. So that's how you connect things. Is there a question? Okay. Properties of this frequency GUI sync. There is the FFT size. The FFT size tells you how much frequency resolution you have. We will do much more about FFTs and FFT sizes probably in the next session. But for today, I'm just going to say that 4096 is my favorite value for this because it looks good on the screen. 1024 is a little bit too low. It gives you less resolution than what's usually needed. And the remaining things, you can experiment with them and learn what they mean on your own. They are quite self-explanatory. So that's the only thing I'm going to change with this. And I have my flow graph. You can see the title is in red. That's because it hasn't been saved. So we can save it with Control S or going here and save. Now this is in black. And there are two buttons here which are important. The first of them says generate the flow graph, and the second one says execute the flow graph. So generate the flow graph, if I click on it, it says I'm generating something, this Python script. So what GNU Radio is saying is I've taken everything you have drawn in here and I have written a Python script for you, which does all of this. And you could use this Python script as any other Python script. You can run it from the terminal. You can even copy it to another machine which has GNU Radio installed. And there is run. Run or execute the flow graph means first generate. So if I have some changes here, I don't need to go and press generate. I can just press execute, and the flow graph will be generated and then executed. So this is how we normally work in GNU Radio. We do things, and then we click play. We see if it's doing what we want. If not, we stop it, and then we change more things, and we click again on play. So that's the usual workflow. And I'm going to click on play. I still have my RTL-SDR stick plugged in. So you can see here it's generating again, it's executing. Let me go back to that window. You can see some log messages that says I'm searching for the hardware, I found it. This PLL not locked, which is a warning that happens at the beginning because the PLL takes a little bit of time to lock. And we can see there is an FM station here. The spectrum plot doesn't look as nice as in GQRX, but nevertheless, we can still see the FM signal. So the thing I want to demonstrate is I have my RF gain, IF gain, and BB gain. These two correspond. Maybe I should do it like this so as to have all the windows in view. So these two correspond to these three RF gain, IF gain, BB gain fields that I've added. And what I can show you is if I put here 30 and press enter, you can see that this increases by 30. And I can put it back to 0. And then let's try the IF gain. If I put it to 30, it doesn't do anything. I can even try 100, it doesn't do anything. So what happens is this RTL-SDR source has an IF gain, but the IF gain really is intended to work with other SDR devices which have multiple gain knobs. So with the RTL-SDR, it doesn't do anything. And then finally, it's the BB gain, and also 30, no changes, 100, no changes. So it doesn't do anything. And this shows you how you can interact with a flow graph which is running. This could be any parameters that you might want to change, the frequency of something, the amplitude of something, anything you can think of, really. And so we have learned that the only thing that matters here is the RF gain, and we can set it to 30 and see all the radio stations. And we could decide what's an appropriate gain in the same way that we did in GQRX. It's basically the same. And 30 dBs in here is the same as 30 dBs in GQRX. So if I go with 60, you can see that it is saturated. Maybe the thing which is not the same between GNU Radio and GQRX is the levels here in decibels, because of how things are normalized, really. So yeah, that's basically how to get data from the RTL-SDR into GNU Radio, and in other tutorials we will do more interesting things. Maybe at this moment I can stop it. So there is this top button which says kill the flow graph. And perhaps something that I can show, and I don't know if that's on the example, no, but I'm going to show it in any case. It's the file sync, because this is a very commonly used block. So with the file sync, what I can do is I'm going to either type in or select with the browser. I'm going to type the file name I want. I don't know, RF recording .raw. It can have any extension name you want. And so far we don't need to touch any of these parameters. It's only if we need to change either the input type or the vector length. And if I go in here and execute, it's the same thing as before, but it is also recording the data to a file. And I can stop it now. And I can show you if I do something like this. Well, there is a file that I have just created, and it has 166 megabytes. So that's something else you should take into account. These files are usually pretty large because they have millions of numbers per second. And this 2.4 megahertz bandwidth is not much, actually. On radio astronomy, it is common to have several hundred megahertz of bandwidth, or even a couple gigahertz of bandwidth in some cases. So yeah, this is like a toy compared to professional telescopes. The thing I can do with this RF recording is I can play it back, even on a different machine or wherever. So I don't need any hardware to play it back. There is a file source. So sync means something that it's an output, and source means something that it's an input. That's the reason that all of these are called sources, and you have file sync, you have other syncs as well. And what I'm doing is I'm disabling this one. I'm connecting the file source to the GUI frequency sync. I need to type in or select the same file. I'm just going to copy and paste. And there is an option to repeat. So that means play back the same recording all the time in a loop, which can be a good idea for some things. And this is a way of doing experiments with some FM radio stations, even if you don't have any hardware, or if you are not near any radio stations or whatever. Making recordings and sharing them for later analysis is something very, very common in digital signal processing. And yeah, this is a signal from the recording. Just as a demonstration, I can unplug this, and still I have this because it's always the same signal I have previously recorded. Okay, any questions? Okay, so that's enough for the RTL-SDR. I also have a demo of how to use audio, because I mentioned GNU Radio is mainly focused on radio digital signal processing, but it can also be used for similar signal processing, such as audio signals. And that's a good thing, because every computer has a sound card, so it has a speaker, it probably has a microphone, and that means we already have some hardware which we can use with GNU Radio for some quick experiments, even if we don't have one of these RTL-SDR sticks. Of course, we cannot receive radio signals with the sound card. We can only receive sound signals. But there are some interesting things that can be done. So let me open a new Flowgraph and let's do some audio signal processing. So I'm going to call this audio demo 2. It doesn't matter in which folder it sits. And the things I want to set here is the sample rate. It needs to match the sound card sample rate, and maybe you already know that 48 kilohertz is a common rate for audio. So we are going to use 48 kilohertz. And then I'm going to use the audio source for the first demonstration. So audio source basically means take the signals from the microphone and put them into GNU Radio. So things to realize: sample rate. I'm choosing sample rate, but you can see here the list of common sample rates for sound cards, and 48 kilohertz is one of them. Device name, you can usually leave this blank, and GNU Radio will choose the default sound card, which is oftentimes the appropriate one. And maybe the first novelty here is this is orange rather than blue. So in here, this is blue, this is orange. And the reason is that this is a real signal. This is really the voltage from the microphone. It is an analog voltage which has been digitally sampled. And there is no IQ data, there is no complex data in here. And that's common with audio signals. We could have two channels with a stereo microphone. For example, I think that's what number of outputs it's supposed to do, but the microphone I'm using, it's not stereo, so one output. And let's do something with it. So what I'm going to do with it is frequency sync. We already know what that does. And we already know that I like to set this to 4096. And I'm also going to demonstrate another GUI element, which is the time sync. Also something else, because I did it really fast and even without thinking. So when I put the frequency sync, it said type complex. And maybe this is something else to point out. If you do a connection like this, the types need to match. So if it's orange here, it needs to be orange in there. If it doesn't match, the arrow is going to be red. That means there is an error. Anytime you see something red, there is an error. For example, here is an error because the input is not connected. And you can see whenever there are errors, I cannot execute the flow graph because it doesn't make sense. It's like a compile error. And there is this button which says view flow graph errors. And if you click on it, usually it has a good description of what the problem is. So for example, the time sync, it has an input and it says the port is not connected. So, okay, I need to connect something here. Otherwise, why would I have a block like this with no input? And then there is some errors about this connection. So audio source, connection to frequency sync. It complains about two different things, which are really the same problem. It says, I cannot connect something which is float, which means a real floating point number, to something which is a complex number. Those are two different data types. Okay, fair enough. And then it's also complaining about sizes, because if you know about sizes of numbers on the computer, a floating point is 4 bytes, and a complex floating point number, has 8 bytes, because 4 bytes for the real part and 4 bytes to the imaginary part. So GNU Radio is saying even if the types are the same, the sizes are not the same. So I do not know how to connect these two. So the way to fix this is many blocks have a type in here that we can set. And I can set this to float. And then I click OK, and it matches. Changing the type is so common that there's a shortcut for that. If you have selected the block, you can press up arrow and down arrow. So the arrows on the keyboard, and that changes the type really quickly, as you can see. So this is up arrow, it goes blue. Down arrow, it goes orange. And I think that's what I did before without even thinking that I was doing, just because I've done this like a million times. So the time sync, we also want this type flow, and 1024 points might be fine. And we will see the difference in a second. This is time sync, so it plots things with respect to time rather than frequency. It's like an oscilloscope plot. So let's go ahead and run this. And what we can see here is that as I'm speaking, there are changes in here on the spectrum. So this is the spectrum of my voice. And you can also see the waveform of my voice. It's moving in here as I speak. This is basically the voltage on the microphone over time. And on the x-axis, you can see the time in milliseconds. So that's 20 something milliseconds, 22 milliseconds probably, 21 point something. That is set by how many points we have on the sample rate. So if we want to have more data in here, for example, 1 second, the thing we can do is we close this and then number of points. If we want to have 1 second, then sample rate multiplied by 1, for example. So there are 48,000 points per second. I want to display 48,000 points in my plot. And then I can click play and, well, you can see it's the same as before, but now you can see syllables and words and everything because there is 1 second of data. And that's the reason why it refreshes every second. Something else to show in here is on this frequency sync, there is both negative frequencies and positive frequencies. And before I was saying negative frequencies do not have a physical meaning. And that's true for a real signal. What happens mathematically is the Fourier transform is symmetric. And you can see that. So everything on the right half of this plot is mirrored on the left half. It's exactly the same thing. So there is an option for displaying only the right half, because oftentimes displaying both halves for real signals is confusing. So what we can do is to get back here, and it says spectrum width, full or half. And you can notice that this option is only available when the signal is floating point, because for complex, the two halves of the spectrum are different. So spectrum width, half. And then this might be more similar to what you can see on an audio editor application or an audio display application. You have 0 hertz in here. And so the basses are here, the trebles are here. And you can realize something about the headset I'm using, since it's a wireless headset and transmitting a lot of data wirelessly is costly. It has a low pass filter, so it's not sampling all my voice. It's cutting it at about 7 kilohertz, because most of the spectral content of a human voice is on this frequency range. But if we had a different microphone, we could see other things in here. And if you have an ultrasound microphone, you can receive ultrasounds. And there are people, for example, who use these kind of things to listen to bats, which use ultrasound for sonar. And that can be very interesting to look at some bat sonar with GNU Radio, or even hydrophones. So you can have microphones inside the water, sonar signals from animals, from ships as well. So yeah, lots of things which can be done with audio. Any questions? Okay, what else can we do with audio? We have a microphone, we have a speaker, which can play back signals. So in audio, there is an audio sync, which is complementary to the audio source. This is the sound card. Any signal which is put in here will get played back on the speakers or headphones or whatever. And let's use that to do an example. of how to generate some simple signals. So the first thing I'm going to do is to change this from complex to float, because we want to, we're using audio, so we want floating point signals. I'm going to copy and paste these two and hook them here. I'll also connect these. And because we have two frequency sinks and two time sinks, maybe it's good to give them names. So that allows me to introduce another thing. Each of these plots has a name or can have a name, and I can write microphone in here. I can also write microphone in here, then sound card and sound card, so that we know which is which. And then I want to be able to change these settings, and the settings which are available. With some effort, I could make something like a selection box to change the waveform, but I'm going to use cosine for the moment. The things I want to change are the frequency and the amplitude, because those are the main parameters of the signal. So entry, there are other things which are not entry. Maybe I should use one of those. So one of them is slider. It's called range. It's a slider, but it's called range. So let me also show how to use the slider. So for the frequency, I'm going to use this thing. And it can have a label, which is the thing that gets displayed. So we can set this to frequency in hertz. And then since it's a frequency, it can be any floating point number. So type floating point. And you might have realized that when I've set this as integer, this is green. When I've set this as floating point, this is orange. Maybe if you are following along in GNU Radio Companion, you don't have these colors and no one has asked anything. So that is an option. You have the option of having colors in the background of text fields representing the data types. It's also written in here. So in here it says real, write a real number, write a string. But you also can learn that purple here means string, orange here and also here means real. And so you always know without reading what type of value you need to put. And I said this is an option, so this is on view. I think that's disabled by default, but I like it. So that's show properties, fields, colors. And if we uncheck it, we can go back to, I think I was on the time something. So now everything is white background. But if I enable it again, we can see, sorry, that was a different one, which is show all block IDs, and it also has some usefulness. But I want to show properties, fields, colors. And there you can see all of these have colors. So you can set it as you prefer. What else I was doing? Yeah, so the sound card and the sound card. There we go. I was on the sliders. Yeah, I was actually showing this one. So data type floating point, data type integer. And off we go with this one. The other thing I want to configure is this thing, which is going to be the amplitude. And I can write amplitude in here. And then I want a default value of 0. The amplitude goes between 0 and 1. That's something which is good to keep in mind. So usually in GNU radio, signals are scaled so that +1 and -1 represent the maximum values that the hardware is capable of, whether it's a receiver or a transmitter, and anything in between is intermediate values. So for example, if you try to send a number which is larger than 1 to the sound card, it will clip and you will get strange sounds. So start at 0, stop at 1. That's the maximum value, and step, I don't know, 0.01, for example. And then we have 100 steps. So that's how we define our slider. And then do not forget that these names need to be written in here. So for the frequency and also for the amplitude. And the main reason yeah, maybe for frequency I want 1000 hertz by default. The reason I've begun with an amplitude of 0 is because, again, I'm going to produce sound and I don't want that to be very annoying. I will just turn it up for the sake of demonstration for a few seconds. So here are all the plots, but since they are like one on top of another, I cannot even see the four of them. So that's another good opportunity to show you something. And that something is how to arrange GUI elements. There is documentation about that on the wiki page, but basically there is a grid and we can write two numbers. So that means first row and first column of the grid, so 0, 0. This one I'm going to put it on 0, 1. So it's the first row, column number 1, so the second column. And this I'm going to put on 1, 0 and 1, 1. This is like given entries of a matrix. And by doing that, I can basically arrange in a table manner my GUI elements. And now you can see it is much nicer. So I have the microphone on these two, and I have the sound card on these two. And these I could also put positions in them. I can assign positions to any GUI element. It doesn't need to be a plot. But they are fine here in the bottom of the screen. So I can now see everything, and it's clearly set up. So at the moment I do not see anything. This is at 0, and that is because the amplitude is 0. I'm going to increase this ever so slightly. Yeah. And you might hear an annoying tone, which I'm maybe going to remove. Yeah, this is tricky because I'm going to do something smarter. So what I'm going to do is I'm going to demonstrate another block, multiply const, which is multiplied by a constant. So this is going to be floating point, and this we are going to call volume. And the reason I'm adding this is because I'm going to have the amplitude controlling here, but I'm going to have an additional volume control, and I will typically keep this at 0 so as to keep annoying everyone. But since the volume control affects only this audio and it doesn't affect the frequency sync and time sync, we can still look at those. So it's basically my way of muting the audio. And I'm going to do that with a slider too. So copy and paste and volume, and I can write anything in here I want. So audio volume, for example. And then what I can do is I can turn up my amplitude as far as I want to. So for example, I don't know, maybe like halfway. And in here I have 1 second, so it's difficult to say anything, but something else you can do is you can draw a box on one of these plots, and that means zoom into that particular region. And if we zoom into that particular region, we can see that it is a sine wave as we expected, because waveform is cosine. And then I can turn up the audio volume just a little bit. So you can see there is some audio. I don't know if it's loud enough for you to even be heard or to become annoying, but it is there whenever I enable it. Other things we can change anything we want. So for example, you can see the frequency here. You can make measurements with the mouse. So it's at 1 kilohertz. And this means my mouse cursor is at 1 kilohertz minus 19.4 dBs. That's where the signal is. And I can write anything. So 2000, for example, and it goes to 2000. And I'm yet going to demonstrate this again. So 2000, You can see it's higher pitch, 1000, it changes now. There is some delay because of how the sound card is driven, but it changes 500 hertz. It's even lower pitch. So that's basically how it works. And you can make much more complicated things with audio and radio playing with these things. You could add filters, you could add more signals and combine them. But for today, I think this is fine. So basically, this is all